Okay, so let's get started today. We were looking at unsupervised clustering yesterday and the Kaggle dataset, the million-song dataset, and we did ETL, explore, and then we're ready to model. So we'll kind of walk through this. In the next example, we will see a lot of the pipeline concepts we're using in much more detail. But here we'll sort of see it slightly high level. Okay. So as I said, the simplest unsupervised learning problem is a clustering problem. And maybe one of the simplest clustering algorithms is the Kmeans algorithm. Okay. So Spark's MLlib, machine learning library's implementation of Kmeans algorithm, expects an input vector for its features. And so what we need to first do is use this vector assembler to take the right columns of the data frame we've been playing with to turn that into a vector. And so that's the idea of a vector assembler. And so here's everything back. You know, I sort of commented a little bit more here. This is our case class song and the parse line function that's done slightly more robustly by doing our own internal implementation of the two-double method, the two-double function, two-int function. You know, of course, you know, here we're just casting the exceptions when our value doesn't return a type double as we expect. So in those exceptions, we turn them into the default value for the double. Which I think might be none or 0, I'm not quite sure. But you can do a lot more. So you can have multiple try catches, or within the catch, you can have case statements and field different things. If the string is NaN, treat it like some other double, and you can even define your own double arithmetic, right? Because formally, something else I do is you know, set valued arithmetic using computers. So, for example, even this gradient descent algorithm we talked about yesterday, I told you it's a heuristic algorithm because it's sensitive to the initial condition of where you start the algorithm. It'll find the path on the steepest descent. But imagine a very simple problem where you don't have just one nice local minimum, which also is the global minimum, right? For some problems, that's the case. But for other problems, that is not the case, right? For deep neural nets, that's not necessarily the case. You know, it's very high dimensional space. So which means, depending on where you start your gradient descent, whether it's stochastic or whatever, it's going to possibly end up in different basins of attraction, you know, different local minima, or, you know, you're minimizing. So which means, you know, you can imagine, say there's like in one dimension, even if you just have two, you know, a function with two valleys, you start on this end, you'll go to this little local minima and get trapped there, right? If you start on this end, you'll trap here. In the middle, well, depending on the details, you could go there or there, right? So that means, you know, there are two basins of attraction, and then you can color all the initial conditions for the right basin as red and the left basin as blue. So that's essentially, you know, what basins of attraction of the Newton operator using real arithmetic. You know, even if you do arithmetic exactly, you will get into this problem. So there are other interesting methods. So it's a diversion where you can actually extend the interval in the Newton operator using interval arithmetic and interval analysis, where your now basic numbers are intervals, you know, floating point bounds that are outwardly rounded, blah blah blah. And now your Newton operator, the interval extension of the Newton operator, can actually start taking a big set. Say you're interested in finding, say, all local optima in a compact set, which is an interval, and then it'll spit out two or more subintervals of that original interval that are guaranteed to contain all the local minima. Okay, and you can iterate this. So this actually is not that hard to visualize. For this dynamical system, you know, which takes each subsets and spits out sets. Unlike the Newton operator in the reals, where it'll take a point and go up, look at the tangent line, come back to the next point and do this, right? So that takes a real and returns a real. this thing will take a real set, a compact real interval in 1D or a rectangle in 2D, and return two subsets, two intervals or rectangles, whatever. And then you can reapply the same operator on these two subsets and it'll branch. So it'll actually be a branching process of sets, right? Those operators can actually be cool because you can now extend the arithmetic beyond the reals by throwing in plus and minus infinities, okay? And plus and minus zeros, and you can actually formalize the art of dividing by zero. Right? This is really beautiful German code, and I mean, it's all over the world. People have done this in Japanese. And anyway, Uppsala University is kind of a hot spot for computed proofs and dynamics and analysis. So anyway, so yes, you can do all that if you really want. Okay, yeah, there's some about. Okay, so we know what happens, and we are going to just run this. We're going to create or replace our temporary view into a songs table, right? So once we do this, this was essentially our other way of babbling between languages, right? Our first way was what? Take a data frame, write it to a simple columnar compressed Parquet files, and then read those Parquet files from a different interpreter, right? Spark or Python. The other way is this one. You create or replace this temp view of the data frame and call it a table. Now this table is accessible in this notebook now. It's a temporary view. And then you can basically use SQL statements from R or Python. That's how we did the ggplot, right? So that's the other way. Okay. So now, so that way you use SQL to just explore and visually, as well as using SQL expressions in all three languages simultaneously, if you like, or no, okay, one at a time. So you're not limited by your sort of Scala's visualization skills if you don't have the gas and get into D3 all the time. Okay. So now we have training data. So the training data is going to be defined by a new instance of this vector assembler class. And this vector assembler class has various initialization things. The first one is set input column. So the set input column is what I'm deciding are going to be the input columns from the songs table that I'm about to transform. And what I'm interested in is the input column given by the array of duration, tempo, and loudness. So there's only three features I'm interested in this really large data set of lots of columns. And then I'm going to set the output columns to this unique name called features. Okay. So, and then I'm going to transform it. And so I'll transform this and create my training data. And I need this vector assembler import. So now you will see, this thing has quite a lot of fields. So all it has done is taken our original data frame and appended new columns to it. And the new column is essentially the features column. Okay. So that's what I've explained there in words. So then if you just take a tree of this training data that we just vector assembled and transform the original table, you can now see that there is this last column added. This is my features column. And it's got these three numbers. Okay, so it's a very convenient way. This way, when you have to go back and re-engineer your features, which is still where a lot of insights are, then you will be able to go and play with different things you pull out from the input column. Okay, so transformers in general is just an abstraction that includes feature transformers and learned models. So we can actually turn models into transformers. So technically, a transformer implements a method called the transform, which converts one data frame into another data frame. It's just pure and simple. So usually you will be appending one or more columns. That's the typical thing of the transformer. Okay. So why would a learning model be an instance of this? A learning model might take a data frame, read the column containing the feature vectors, and then predict the label for each feature vector and output a new data frame with another column added to it called the predicted labels column, right? So you just can append more things, transformers. So of course, if you use the model for prediction, then the transformers are great. What is an estimator? An estimator abstracts the concept of a learning algorithm or any algorithm that fits the training data using a computer. Okay, so it's the statistical learning theory notion, estimator. And the method it uses is fit. So whatever is the appropriate optimization technique for that class of models, it will use that. And depending on the sizes of the data, it will choose some default values for batch sizes and things like this. You can go and play with all of those settings. Okay. So concretely, we are not seeing the logistic regression example, but logistic regression is essentially a classifier problem where you usually have only two classes, and it's it uses this logistic function to assign, say, spam or no spam. And the logistic regression in this case is an estimator, and calling the fit method on it will train this logistic regression model. Okay. So let's just play here. So we just display the training data, and we select these 3 columns, and then I limit it to 5, and I'm using Databricks to display this. So here's my feature vector. So if you look at this triangle, it'll just tell you it's an array where the first element is 1, the second element is 3, and so on. We'll come back to this. So this is whether it's a sparse array or a dense array. And so that's essentially the input we need to send to the algorithm. Okay, now I try to do this on the blackboard because we had technical problems yesterday, so we only had one YouTube cast. So let's sort of go through this quickly. This is just a hash of Wikipedia. So, yeah.
Where did the 1 and 3 come from? Because the features was only 4 features.
All right. So you just look at this for now. Yeah, it's the one they're encoding. So we'll get into this in the next example in detail. But this is so 1 says it's a dense matrix. 3 says that's the length of the array that is dense. And I don't know what this says, but we can read that later. Okay. So later on for handwritten digit recognition, which we'll do maybe after Fika, Tilo forgot to get the Fika bread, so he's gone back in the bus, so maybe we won't have Fika. You guys are welcome to bring Fika. It's coming out of my pocket, right? So, and Tilo, so feel free to organize. That's what the meetup is there, right? I'll bring Fika today. Or my wife's refusing to cook breads anymore. Because we were in Christchurch when the earthquake happened, right? So you guys know about this? It's a 1-minute detour. So in 2011, it was a massive earthquake in Christchurch. The whole city was shaking for literally a year and a half. Lots of people died. It was just before the big tsunami attack in Japan. They're coupled systems. So anyway, the students in the university shut down for like 2 weeks, and then we started teaching on tents on the parking lots, because we wanted to keep the university running. So that's when I started getting to YouTube lectures, because we all had to do some kind of screencast from home, right? But then the students all kind of organized, and they created something called the Student Volunteer Army, and they helped clean the city because it was just massive destruction. So, and then my wife and a bunch of neighbors, they were all part of this, what is it called? A baking army or something. So they baked food for the kids. Anyway, so this is not as important as the earthquake, so my wife was not going to bake Fika bread for you guys. That's the moral of the story. All right, so shall I proceed with the standard algorithm? Okay, so standard algorithm is the following. We have a bunch of points. These are these gray squares in 2 dimensions, which is 2 vectors. And then I have some initial conditions. So for me, k is 3. I have just 3. So I have 3 initial conditions, calling my first cluster, say, green. This is my second cluster, red, and this is the third cluster, blue. So I just throw some points at random. That's called the initial condition of the Kmeans algorithm. And then what we do is just the next iteration, we simply look at each of these points and find the distance to every other cluster center, and then choose the closest cluster center as its membership. So all these guys are green because they're closest to green. This guy is the only one that's closest to red, and these guys are closest to blue. And then what are these lines? So this is so we have a pure math guy, so I'm going to kind of have some fun, right? So this is a Voronoi diagram. So this is essentially coming from this partition. And I wanted to point out that this Kmeans algorithm, you were saying yesterday, is just two clusters, blah, blah, blah. So I told you already about this, right? A probabilistic theory of pattern recognition. It's kind of really beautiful. So there's DeVroy wrote this book very recently. I just started reading it. And so this is lectures on the nearest neighbor method. This is another extremely powerful method, which Kmeans algorithm is the simplest example of, right? So nearest neighbor methods, as well as other things. So this has everything about trees and partitions we'll get into. So there is this really nice book called Combinatorial Methods in Density Estimation. So why is all this important, right? Why do we have to pay mathematicians, right? So it's important because the combinatorial complexity of the sets you're creating, say in this example, to create these partitions, okay, directly enters into what is called the rate at which you can learn. It directly determines the rate at which you can learn without overfitting. So you still allow for generalization, generalizability, right? And the way it actually enters is, for those with some probability theory, it's the rate of convergence of the empirical measure. So what's an empirical measure? Empirical measure is just the raw data, right? All these points have fallen. Just imagine them as points in some space, and they're little pins, okay, of height, whatever, 1 over n. So all these pins are just stuck. That's the empirical measure. That's all we have, right? Maybe it's continuous data. Then you can say, oh, well, maybe it's a density, okay? Because we cannot talk about exact hair length in angstroms even. Because, as you're measuring it, my hair might grow. So it's more weird, right? So you need to talk about the point being inside a tiny little box. And that's, if you're only interested in what is the probability the point lands in a tiny little box, that's essentially a continuous random variable, right? So if you do that, then you have something called this Lebesgue-Stelji measure, which is no biggie. All that says is, I'm really only interested in the probability that the point lands in a tiny tile. So what I'm going to assume is that there is actually some density, some function sitting on this, okay? So that if I integrate, if I find the area under that curve over this tile by chopping it like mad, and looking at Riemann sums, or more complicated, but basically that gives you the probability of the point falling in that little ball of epsilon, radius epsilon or tile. So that's kind of this continuous random variable. So you can assume that they have a density, but often you can't. Then you will assume that they what are called atoms. So they actually could be possibly a mixture of a continuous density with atoms, right? And this is so financial engineering, which is all scalable now. You do these kinds of assumptions because maybe even Swish transactions, right? Swish transactions or whatever. People give $10 for coffee or maybe whatever. So there'll be like lots of events falling on 10 krona, right? Also, there's no 0.1 krona, right? So you guys don't have penny which you can melt in your own vats with enough wood and put it into ammunitions and take up arms against your government. Americans do this. Anyway, my point is, I'm just jazzing. My point is, you can have discrete measures mixed in with continuous measures in the full-blown setting, and the rate at which. So that means now, what is statistical consistency? So statistical consistency says that under my model, which all models are wrong, but under my mathematical model, probabilistic model usually, of what I think is happening, what I want to be able to say is, as the amount of information approaches infinity, right? As I'm observing more and more, as much as I like, right? What is the rate at which the empirical measure, these points landing everywhere, converges to the true measure? So true measure is probability measure, right? What's the probability land point falling in a little cell? So, and the empirical measure basically is, in that cell, how many points have fallen, right? Say 3, divide by 800 million. So 3 by 800 million is your empirical measure, right? That's all you have. But so what's really, really important is, as a function of how much observations you have, which is little n, okay, how quickly does the empirical measure converges to the true measure under your model that you don't know? You get it? right? How quickly it converges is very, very important because you want to make sure that you don't overcomplicate these tiles, right? So I told you little tiles, but now these are Voronoi diagrams and they're more complicated objects. So at a very, very high level, the combinatorial complexity essentially is something very interesting because you have geometry and so on. And so you want to know how you can start partitioning arbitrary sets of size k and with n samples and blah, blah, blah. And that's enough, okay? So that's, so I like mathematical statistics. That's sort of my thing. Okay, so now in the next step, what's happening, I now look at the centroids. I mean, the mean of each of these green points in each coordinate, and I get my centroid, which is this new green thing. So my old green thing is this dot, dot, dot. It moved to the new green thing. It's the new updated centroid, right? And then, and of course, this red guy only had one guy. It's a lonely guy in the cell. So he just, his mean is himself. So, or she moves there, okay? So, and then the same with the blue. Blue slightly moves here. So then you iterate this, right? And you play this game. Now you look at the Voronoi diagram for this configuration of these centroids. Then you get, so what's happening is as this, and then you keep doing this until the blues and the reds and the greens barely start moving. You stop. Right? So what are the main things to bear in mind? This whole algorithm is sensitive to the initial condition where you threw the red, green, and blue to begin with. If you throw it in different places, you'll get different convergence, right, of these points. So that's important to bear in mind. There is actually a probabilistic model under the hood here, right? So what's really you can say is my points are actually coming from a Gaussian distribution or a bivariate normal. Normal is Gaussian, right? A Gaussian distribution in 2 dimensions with unknown means, right? And the variance is spherically symmetric, so there's no ellipsoidal structures, right? So just variance covariance matrix of basically 1. So then I'm interested in explaining this data as the maximum likelihood or the best explanation of 3 means, right? Mu1, mu2, and mu3. Mu3, they're in 2 dimensions each, right? I want to know what the centers are for these 3 clusters that come from spherically symmetric Gaussian distribution. That's the probability model under the hood, and this is actually a heuristic algorithm to find out the best fit there. Okay, so this is, oh yeah, maybe I should have just shown this. Look at that. So this is just straight out of Wikipedia. And there's a lot of exam, you can just knock yourself out. All the stuff I'm blabbering is here, the initialization method. Okay. Now let's just look at a caution. So we're of course in, so I really like plant taxonomy. It's one of my favorite things to do, especially after a lot of maths because it's good for your eyes. And Linnaeus, he's from here, so he started the Latin taxonomy system, right? Linnaean taxonomy is what we have. So under Linnaean taxonomy, you can go and look at the flower, understand its biology and who it mates with and blah, 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 and actually know which is which species, yeah? So with a lot of detailed taxonomy and fieldwork, you know that there are actually 3 iris species, Iris setosa, Iris versicolor, and Iris virginica. And they're given by these 3 keys. And what I'm looking at is their the various sepal lengths, I think, like the shapes of their flowers and various measurements of their flowers. That's what's shown in these 3 axes. Okay, so the Kmeans algorithm, gets this wrong, for certain initial conditions, right? So you run the Kmeans algorithm under some default initial condition, and it says that these are my 3 clusters: blue, red, and green, right? And of course, this is the truth, right? So you need to know that it's just a clustering, and it's sensitive to initial conditions. And so clearly, using the K-means algorithm and coming up with clusters, and then saying those who belong to this cluster are a given species, biologically meaningful species, is kind of bad. let's see. So here I'm basically going to now take our training data, which is nicely formatted with the vector assembler, and I'm going to have a model, and I'm going to have a new instance of this model called Kmeans, a specific model, and then I'm setting K to 2. This is one of the parameters, and then I'm going to just fit it to the training data. So I'm not sure how long this will take. It took 37 seconds in academic shard, it's slightly more beefy than this one. Okay. Oh, 13 seconds. Okay. There's a lot of other computations running on the other shard. Okay, so now you can do this. Okay, so if you want to know what are all the different methods implemented on the model you just fitted, K-means, there is a lot of stuff, fast instance soft clear, blah blah blah. It's quite a lot, and you can knock yourself out in the documentations, latest documentations for Spark. But let's look at this one. This is cluster centers, right? That sounds interesting. So here is, let's get the cluster centers. So now I know for this, now we're back to the 1 million songs example for the 3 features we picked. So we have 2 cluster centers because we set K equals 2, and each cluster center has 3 dimensions. So now, remember I said we can apply the transform method to the model, and so we're going to just do this. This is kind of a bad nomenclature, but all we're going to do is we're going to get predictions as the last column. Predictions basically will say which cluster each of the training data rows belong to. Okay? So it's not predicting in the usual sense. It's just so here's my data frame, the training data. So let's just print schema. Just to recall, we have features, and we just took 3 of these earlier columns, and then I have my model that has been transformed, and you will see that oops, I go into that cell and go down. I have another column called prediction, and it's just an integer valued column. So this column is just going to say, after the algorithm ran, which cluster each data point belongs to in the end. Okay. So now, because this model transformed is like a ugly monster with so much details, we're only interested in 3 things we used for the features: duration, tempo, loudness, and the column of prediction, which is where does each song go to. So we can do this, and we can simply use the display function or .show if you're not on Databricks, and you can see it. But remember, this was a fairly large data set, right? So so I already forgot the size. 1 million? Yeah, so 1 million, exactly 1 million? Oh yeah, it's 1 million songs. I'm just like running on like negative sleep now. So wait, oh yeah, so yeah, well, oh yeah, we didn't do all the 1 million, right? So we only had 31,069. Okay, so let's, yeah, because that might take longer on the on this community edition. So now we have just sampling the fraction. So we are just going to take, this is what I said earlier, like especially if this is very, very large, you may want to take, use this method, .sample. And this just says, give me sampling without replacement, right? So it's a whole bunch of balls in the urn. Each ball is the row number. And I sample, if it's well stirred, I sample one at a time. And I don't put it back in when I sample the second one. Right? So it's just a random subset of this fraction. So this is 0.005 times 31,369. Okay, so that should be the number of rows here. So let's just take a look at this. Just a few. So we know songs with this duration, tempo, and loudness are predicted to be in the first cluster, and ones like this are predicted to be in the second cluster, because the cluster labels start with 0. Okay, so that's that. Now, what does this mean, right? So your boss will say, so what? So then you say, okay, I'll show you some pictures, right? So I mean, yeah, it's important, right? So this is, I mean, data science has very important soft skills, right? So I'm just basically taking a slightly larger fraction, and I'm going to just use this scatter plot display. Yeah. So yeah, those are the. So then I can see what's my. So if you look at what I've done here, you look at plot options. So basically, take the values to be loudness, tempo, and duration. So that are my 3x3 pairwise scatter plots. And I take my keys to be prediction, and I colored my keys, right? And I just my display scatter plot. Okay, so so now what can you tell? This looks good, right? The loudness versus duration. I mean, it's a clean split. I don't know. Looks. This also looks good. Tempo versus duration. I'm not saying that ABBA and certain kinds of ABBA people fall in this or not. You want to really, yeah, you probably have to go work in Spotify and figure out people's mood when they walk fast and slow, depending on their GPS trajectories they allow the app to use. Okay, you're not going. But yeah, it's the idea, right? But now look at this, tempo versus loudness. Right, so it's kind of mixed, right? You see blues and yellows sort of mixed in. So this is sort of the punchline here. So there's very little correlation between loudness and tempo in the generated clusters, right? So that's this one. So let's focus on the panels in the first and second columns of the scatter plot. So for varying values of loudness and tempo, the prediction does not change, right? So varying values of loudness and tempo, we have yellows and blues mixed up. So how are you going to explain that to your boss? Problem, right? So we want to ideally, at least these three are very sensible coarse projections of the actual song. So it'd be nice to do something to. So then to make sense of this, first thing you could do is just to look at the marginal distribution of duration, right? So what I mean by the marginal distribution, just duration by itself as a histogram, right? That's okay. So let's do this. So this is what I've done. So I've basically picked the histogram from the plots menu and the plot options, and then I chose the prediction as key and duration as value. So what you're now able to see is that there is a skew, right? The histogram plot shows significant skew in duration, right? So you see, okay, so just to make sure, it's no magic. And all of this is babblable across notebooks and stuff, just like slightly different HTML display operators. So, so you see, some songs have a very, very long duration, right? So in cluster 1. And in cluster 0, it's different. So we have to somehow correct for this, okay? So, I mean, there's a lot of techniques and clever people working on stuff like this. And feature engineering was a really hot thing for almost a decade until recently. It still is. And one thing we can just say is, okay, I just want to squish things toward 0, right? So I can just maybe apply the log function. So it's so things that are far away, it's like the Richter scale, right? It should. So let's try that thing. So now I'm going to do the following. This is a very, very powerful SQL operation that is immediately pluggable into feature re-engineering operations for the machine learning pipelines. It's super nice. So you can do select expression, and you can do this in pure SQL as well. So I'm just going to do this in data frames, tempo, loudness, and then I want log duration as log duration. So it's going to create a new column called log_duration, which will be just the logarithm, the mathematical logarithm of the duration. And yeah.
Do you take the log because there is a difference between 0 and 1 in the plot that you plotted before in Command 29?
Yeah, so because I just noticed that this thing, no, okay, so this, what does this say? This says, correct me if I'm wrong, right? So it's very important. It's a waking check. So this says, what I think this says is, I'm looking at all the, I'm looking at all the data points that were in cluster 0, according to the terminal point of the Kmeans algorithm, and all the points that are at cluster 1, right? And for all these points, which is actually 3 columns, right? I'm only looking at the duration, the second, I don't know which column. That's what I mean by the marginal distribution of the duration for each cluster. That's just what we're looking at. And what we notice is, in this guy's world, the durations are kind of clustered around here, quite small. And this is the same. You can look upstairs here. So like there's a few songs, few is like not just 1 or 2, a few songs with quite a large duration. So this statisticians would call this a skewed distribution. So what I would like to do is to apply, maybe you haven't seen it, but the standard thing to do without thinking too much is to apply some transformation to the duration feature. And this I'm going to call my new feature, which will be logarithm of duration. So things will squish, you will see in one more slide, and then you will see it will partition. Right? So these things will be moving here, right? So that's, and these two, right? But they won't move as much as these will move. Anyway. So that's basically this. But look at this simple pipeline construct now. I go back and I do training data too, just to make it a separate immutable. I have my new instance of my vector assembler. So I'm doing everything now. Into my vector assembler, I set input columns to be the same as before. And then I'm setting the output columns to be features, just like before. And I'm transforming the input data frame, just as before. Nothing's really different. And then what I've done now, the main thing is log duration. Yeah, so that's why it's training data too. So we have log duration now. So everything is the same as before, except the first column is log duration. Now I do exactly the same, but I create model 2, and I do the same, 2k is 2, fit. And I have done my predictions. So that's the other transform. And then I'm sampling a fraction. If you're really paranoid about, which you should be, what I would do is I'd control the seed of the pseudo-random number generator that's controlling the sampling itself. So you look at exactly the same pseudo-random sample between the two things, but this is small enough. Okay. So that's basically what's going on. So now I look at this and let's see. So here's my log duration and my tempo and yeah, I think the plots log tempo log duration log duration loudness tempo log duration. Okay, so let's see what happens here. Here, so now tempo and log duration are split, and so the new clustering model makes much more sense. Supposedly, it doesn't make sense to me right now, but songs with high tempo and loudness are put in one cluster, and song duration does not affect song categories. Okay.
So but then I lost the relation between the duration and loudness, because previously there were a category, a clear distinction. So is this normal or?
I mean, so this basically squashed things close to here, right? Between 4 to 6 minutes now.
Yeah.
So so between tempo and log duration, it seems like we can split like this. Yeah. And so let's look here between tempo and duration. I don't know, we split this way.
No, I mean that between tempo and loudness, there were a clear split, but after the log transport, we lost this clear.
Yeah, but then we got a clear split between tempo and loudness, right?
Can we have
okay, so let's make sure. Tempo and loudness. You see, the problem was this was smeared. So now that's not smeared, right? Okay. So that's why, because we did the log transform of this duration, right? Because it's a partitioning is happening in 3 dimensions. It's just an example, right? I'm not like I'm not really saying anything. I just want you to understand that we split, and you engineer features, you lose some splits, you gain other splits, and okay. Yeah.
But you don't necessarily need a correlation between like duration and like loudness.
Yeah, so correlation is really bad. Okay, so correlation is actually it's like a multiple many-to-one mappings of what people mean. I just mean like blue. So all I mean is this, right? I just meant like these orangish points and these bluish points. It's almost the Swedish flag colors, right? In this picture are clearly split, right? And in the other picture, they were not. That's all I'm saying by the word correlation in this instance. Okay. Yeah, it's not just this linear correlation, or correlation can be defined on an arbitrary point set in 2 dimensions, right? All right, so this is just kind of a warm-up, okay? So what I want to do, something real, is this one, okay? And right, okay. So we will be doing supervised clustering with decision trees. So now we are in the, so you have some idea of partitioning stuff. And in that case, we had no idea what the labels were. We just threw some things and just did some clustering and then called them to belong to different clusters. Now what we're going to do is, there are experts working in a post office who have taken a lot of handwritten digits on envelopes and took photographs of them in grayscale and marked, oh, this is a 6, this is an 8, and so on and so forth. So there was a teacher who decided what digits from 0 to 9, handwritten digits, what the actual digit is, right? That's the input data. So this is a supervised setting. And what we're going to do, this is a very standard thing that people do in machine learning. This data set is like overfished, but it's a nice example. Okay? So we're going to basically learn about how decision trees will be used for handwritten digit recognition. And yeah, so right. So before we get into this, let's do one link in a new tab and give you guys a visual introduction to decision trees. Okay, this is one of my favorite interactive animation. It won some award. Has anyone seen this? Ah, cool. So I think this is some collaboration between an artist, digital artist in New York City, and some graduate student at Stanford, I think. it won some award. Okay, so what is the problem? So we want to essentially take data about features of houses in San Francisco and New York City, right? And try to learn something, build a model. And then when a new house feature comes in without the tag which city it is in, we want to predict which city it's in. Okay, that's the problem. So here's some intuition. So San Francisco basically is green and New York is blue, right? So what I'm showing you is now just the elevation. So we have on the y-axis the number of feet. So this where the house is located above sea level. So this is 239.5 feet. Well, this is New York City, right? San Francisco is hilly, so we have quite a lot of feet, 744.8 feet. So that's just one feature of this of the houses. So the question is, if we just use this feature, how would we classify just one feature? But if we add another dimension, it allows for more nuance. So we can now say, let me look at the how much it costs per square meter. So now I have elevation on the y-axis and how much it costs per square meter on the x-axis, right? So so I just had elevation here, and I'm now bringing in the other feature. So you can see some pattern. So so you guys know what predictors are and variables are, and these are really good links, so you can hover over them, and it just tells you a lot more. Okay. So now what we want to do is maybe we're going to draw boundaries. Okay, so we're going to say, okay, let me split by elevation at this point. So I have all of these things in green because this is San Francisco, and let me split it here by price per square feet. Then all these things are New York. Okay, and it's getting maybe a little bit better. Right? So you can visualize your elevation to be more than 73 meters, and price per square foot to be more than 19,116. Right. So these are my my split points. So if I split here along this axis, okay, I first split here, and we divide this in two, and then this cell, right? I'm going to split here. So then I'm creating my cells. So maybe we'll stop even if there's no fika bread, just to recharge, and then yeah.